Okay guys, so we're going to talk about buffer capacity, and then we should be pretty much at that point through most of what we're going to talk about when it comes to acid and bases for this unit. Okay, so with a buffer capacity, the idea here is that anytime you have a buffer, there's only a certain amount of acid or base that you can add to that buffer before it starts to immediately lose its ability to maintain the same pH. So its capacity is just the amount of acid or base that a buffer can neutralize before the pH begins to change to an appreciable degree. Okay? So when we say an appreciable degree, typically it's going to go out of the general pH range of a buffer, and that typically is usually about 1 pH unit from the pKa. So essentially what that is that after we've gone past that 1 pH unit, typically what you'll see is either, or if we're adding more base, it's going to see a lot of an increase in pH. If we're adding more acid, we'll see a large decrease in pH. Okay? So how are we able to use this idea to be able to calculate for a pH change when we add a certain amount of acid or base to a buffer? Well, that's what we're going to talk about now. So we're going to solve for a pH change in this situation. And how we do that is first, we're going to find the moles of OH from the molarity equation. Because what we're going to add to our whole what we're going to add to our to our equation, to our chemical reaction, is going to be the hydroxide ions. Okay? Next, we're going to determine the limiting reactant. And that's where we talked about that in unit 5. So we should be experts at this point in determining the limiting reactant. If we still need help, please let me know. Okay? Then using that, we're going to determine the change in the number of moles for the acid and the base. Okay, so you need to know the number of moles because for the next step, we're going to go ahead and find the new concentration for the acid and base using the molarity equation. Okay, then we're going to assume that the pH that's given is at equilibrium. And when we do that, we should note that at equilibrium, our pH will equal our pKa. That's why we use Ka to find our pH and vice versa. So therefore, at equilibrium, we're going to assume that that's the pKa. So now we have our pKa. So now we have our concentration for our acid and our base, and we have our pKa. Those three things indicate that we are going to be using the Henderson-Hasselbalch equation. So using the Henderson-Hasselbalch equation that you were given, determine the pH. And again, we want to round to 2 decimal places. Okay, so let's go ahead and do that. So this is all going to be for moles, so let's go ahead and write that in so we don't forget that. Okay, a buffer is made by adding 0.300 moles of CH3COO, acetic acid, okay, and 0.300 moles of acetate, and enough water to make 1 liter of solution. The pH of the buffer is 4.74. What is the pH of the solution after adding 5.0 milliliters of 4.0 molar NaOH? Okay, so we first need to determine, using our molarity equation, what the moles of NaOH are. And that's simple, right? Remember? So what you're going to do for that is you're going to multiply this, and remember we have to convert that to liters. So we would take 5.0 divided by 1,000 to get us 0.005 and multiply it by 4.0. And what we get is 0.020. Okay, so that's our concentration of OH. Here, it's going to be 0.300 and 0.300. So now my next step is to go ahead and determine my limiting reactant. So I do that. Remember, we do 0.300 moles of acetic acid. Take 1 mole of acetic acid. And since I'm going to this is going to be more my measurable product for our purposes here, let's just convert everything to our acetate as well. Okay, so therefore we see we've got a 1-to-1 ratio, so we're going to have 0.300 moles of CH3COO minus 1. Okay, now we look at our second reactant here, our hydroxide ion. So we're going to convert that one to acetate. And again, we're going to see a 1-to-1 ratio. Okay, so when we look at that, which one is less? Obviously this one is. So this is our limiting reactant, which means that hydroxide is our limiting reactant. So whenever we have a limiting reactant, that's what's all going to be, that's what our change is going to be, because that's what we're adding into the system. It's going to completely react and go away to allow us to go to equilibrium. So we're going to subtract out, because we've added in here, so per our Le Chatelier's principle, everything's going to move to the right. Okay, so we're going to subtract out 0.020, and we're going to add 0.020. Okay, so that should be 0, obviously. We should get 0.280 and 0.320. So now we're going to find our new concentrations of our acetate and our acetate and our acetic acid. Okay? So, remember, we're going to be doing it moles per liter. So we want to know what the concentration is of CH3COO. That's going to equal moles over liters. Well, we already have our moles. That was 0.280 moles. We had originally 1 liter, but we've added 5 milliliters. So now we have 1 liter and 5 milliliters added together, which is 1.005 liters. Okay? Put this into your calculator and you should get your new concentration of acetic acid. Okay, we're going to round to 3 decimal places. Well, I should say 3 significant figures. Okay, now we're going to do the same thing for our acetate ion. And again, that's just going to be moles over liters. Okay, we know what our moles are because we just calculated for those. And I just told you that we have a new volume. So when we put that in, and again, we need to round to 3 significant figures here. There we go. So that's our new concentration of our base. So this is the acid, and this is our base. So now we can use the Henderson-Hasselbalch equation because we know what our pKa is. Our pKa from our question, because remember we assumed that the pH given is at equilibrium, is 4.74. So we're going to put in pH is equal to the pKa plus the log of base over acid. So our pH is going to equal 4.74 plus the log of our base, which is 0.318 all over 0.279 over our acid. For our pH, we put that in. And we get this for our answer. Remember, we're rounding to 2 decimal places, so 4.80. And that's just pretty simple, and that's how you solve for a change in a pH when you're dealing with a buffer. Okay? So, now let's look here. We're going to go to our next portion, and we're now going to take a total 180-degree turn and start talking about solubility equilibrium. And this is kind of important to understand. So we talked about solubility rules when it came to, in Unit 6, when it came to determining whether or not something will be aqueous or whether it'll be a solid when it's in solution. But those things that we said would be solids, they're not necessarily always solids, okay? And what that means is that they can go back and forth from their ions to their solid solids as needed. So kind of in a very, 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 very slow reaction. So it's why it looks like a solid to you, but it's actually going back and forth. And this is where we get this idea of equilibrium when it comes to solubility. Okay, so the first thing we're going to talk about is the solubility product. And this is KSP. And essentially what that is, it's the equilibrium constant that indicates how soluble the solid is in water. In order to do that, we need to have a saturated solution. And that essentially is a solution in which the solution is in contact with undissolved solid. So essentially when we have a saturated solution, if I add any more solid to it, any more of our, precipitate, or I cause for more precipitate to come out, it's going to drop out of solution as a solid from there on out. I cannot add any more. I cannot add any less. Okay? So when we look at this KSP, how are we going to write it? Well, remember, solids we don't include in our equilibrium constant. That doesn't change just because we're naming it something different. We're calling it KSP instead of KC. Okay? So if I write that out, I write KSP. I'm only going to write what's aqueous. Well, what's aqueous is my concentrations over here on my products. I don't have any reactants that I can include in my equilibrium constant. So this is how I would write this one. Okay, so that's how we write KSP. Now, some general rules for writing KSP. Okay, and we have a general rule that kind of helps us, make sure that we write the same thing. Okay, and that's that the solubility product KSP of a compound equals the product of the concentration of the ions involved in the reaction. Each raised to the power of its coefficients in the equilibrium equation. So an example here, again, this should be solid, okay? So, again, KSP is going to equal Ca plus 2. And then we're going to have F minus 1. Because we have a 2 here, we have to raise that to that 2, and therefore we have F minus 1 squared. So it's very important that we write those in. We cannot drop these. We were able to kind of do so in the last portion with all of our KBs and KAs because I kept everything for you guys with the same that they all had a coefficient of 1. But we're not going to always see that with these solubility products, so it's very important to remember that we do need to raise them to the coefficients of the balanced chemical equation. Okay? So if we're going to solve for KSP, what do you think the first thing we're going to do is? We're going to first write the solubility product equation. 2, we're then going to make an ICE table. Remember, and ICE stands for initial change in equilibrium. Then we're going to plug in all values into the ICE table. And you'll notice something that I did on our ICE table. You'll notice that I grayed out the areas for our solid, and that's because they don't have any effect on equilibrium. So you do not need to plug in solid concentrations, because solids don't really have concentrations. So don't even worry about it. You can black it out like I did. Okay? 4, you're going to find the change in equilibrium concentrations. And then 5, using the new equilibrium concentrations and the solubility product equation, you're going to find your KSP. Okay, pretty simple. Shouldn't take us too long. This is probably going to be easier than even what we did with the acids, okay? So, first thing we're going to do is look at this. At equilibrium, the concentration of silver ion, Ag+, is 1.3 times 10 to the negative 4th molar. Assuming that the silver chromate solution is saturated, calculate the KSP for the equation. Okay? So first thing we're going to write is our KSP, solubility product equation. So KSP is going to equal Ag plus. Remember, we got to square that because it has a 2 right there. And our CrO4 minus 2. Okay? Now remember, when we're looking at our ice table, I don't care about this because it's a solid. It has no effect on my equilibrium, so I'm not going to worry about writing it. So instead, what I'm going to write is my initial concentrations, which if my initial concentrations of this, they should be, I'm going to assume that they are 0. Because I'm going to assume that I had this, which is a solid. Okay? I'm going to assume that I had this situation, and I just put this into solution and let it dissolve and break apart as much as it could. Okay? So, if I'm going to be moving to the right, I need to add 2x, because I've got 2 of those. Okay? And x. And I've already know what my equilibrium concentration is for my silver. It's 1.3 times 10 to the negative 4th. Okay? And then this is just simply x. So, now I'm going to figure out what my concentration for CrO4 is minus 2, the chromate ion. Okay? So my Ag plus 1 is equal to 2x. Okay? So I already know what that concentration is at equilibrium. It's 1.3 times 10 to the negative 4th. That's going to equal 2x. So what I need to do is I need to divide by 2 on both sides, and that should give me my x value, which is going to be 6.5 times 10 to the negative 5th. Okay? If I say that my chromate ion is just going to equal x, well then my chromate ion's concentration should be 6.5 times 10 to the negative 5th. Okay, and this is going to be molar. So now to find my KSP, I just plug everything in. I get KSP is equal to Ag plus 1 squared times CrO4 minus 2. So it's my concentration of silver ion squared and my chromate ion multiplied by my concentration of my chromate ion. So my KSP is going to equal 1.3 times 10 to the negative 4th. This is going to be squared times 6.5 times 10 to the negative 5th. So my KSP, when I multiply this out, so remember we always want to use as many parentheses as we deem necessary. So if you're overusing parentheses, you're not using enough. That's what I like to say, remember? In my calculator. Okay? So, we've only had 2 significant figures, so it's going to be 1.1 times 10 to the negative 12th. Okay, so this is where we're going to stop for this one, and then we're going to finish up with the last couple pages of this packet on the next video.